Presentation, I will take you through how we embraced Kafka to solve the challenges around our business operations. So let me take you through what Yubi is and what is the role of business operations team there, and then I will get into the challenges and how we have solved it. So Yubi is basically a debt infrastructure platform. So we are trying to digitalize the lending arena. So we sit in right in between lenders and originators. On the other side, we have borrowers. Lenders basically are the banks and big NBFUs, as well as originators. We have retail investors, as well as small NBFCs. On the borrowers, so we have the borrowers. So we have different kind of loan structures. So one is the co-lending, so where lenders and originators get into a partnership and they will disperse the loan to the borrowers. On the other side, we have pools. So pools where direct assignment and PTC transaction get into pools. Let's not get into details of that. And Aspro, this is basically a B2C platform. This is a trading platform for bonds and Acumen. So in Acumen, we have information about institutions, listed institutions, their ratings, as well as their financial statements. So any lender, before getting into an agreement, they can use this platform to check the details and the financials of the institution before getting into an agreement. And user. So user is actually data as a service platform. So once we get into an agreement with any lenders, so we have their data. So instead of providing regulated reports to them, we will expose their data through a dedicated workspace. So they can access their data in the way they need it. So that is what user does, and we have Spark2. Spark2 is, again, it's a complement to the lending platform. So Spark2, we are trying to digitalize the collections area. Now let's see what business operations does. So even though we are digitalizing the lending platform, so there are areas where due diligence is needed. We have bonds. If you take for bonds, few of the tickets which involves few crores of rupees. So some tickets will come around 5 crores or 6 crores. So for that, even though the ticket is processed through our platform, due diligence of the business operations team needed. So business operations team, so we have different verticals. So they know the business, but they are not that much technically savvy. So so whenever such big ticket transactions are happening, the business operations team will be involved in that. They have to approve those transactions. For this, they need to go through data in different sources. So that is business operations. And on the loan side also, so loans has to go through different stages. Like before post disbursement, there are multiple stages. And after disbursement, there are multiple stages. So after disbursement, you can take so when a loan has been disbursed, we have originators as well as lenders. There is a split going to happen, and this business operations team has to pitch in and check whether the split up has been as per the agreement. So there are multiple places where business operations team has been involved. So what is the challenges? Let us see here. So this is the typical architecture. So as we are into the fintech, so we have to give lot of reports in an automated way. So every day we have to give the collection details to the our lenders, our clients. On top of that, consider, so we have banks like Axis or HDFCs. They have their very good infrastructure. So we will include our system into their infrastructure. So there won't be any issues. But there are small NBFCs. So they don't have that infrastructure. So they use Yubi system as their loan management systems. So as they are into our system, they will ask for too many ad hoc reports. So whenever any transactions or whenever any loan dispersal is happening, they immediately come for the report on that. So those clients, so this blue line represents the ad hoc report flow. So clients will raise a request through a ticket, and that ticket will be received by the business operations team. So once the business operations team receives it, they will just forwards the ticket to the, so if it is related to a product team, it will send to the product team. If it's related to data, then it will come to the data engineering team. So what we does is that, so whether if those reports can be easily fetched from data warehouse tables. So data warehouse tables is the D-1 tables. If they can be fetched from there, we will fetch it from there and we will pass it to the client and we will close the ticket. Or else through batch operations, we will fetch from the relevant sources. Again, this batch operations takes time. So this is the typical flow of automated reports as well as ad hoc reports. Now, the challenges what we are facing here is that, see, whenever a report comes, they have a dependency on the data engineer. So few of the reports might be, they need it very soon because something might have happened on the client side or some, as it is fintech, there might be so many audits which is happening on the client side, so many ad hoc reports might be coming. So when it passed through the data engineer, the priority is getting dissolved. The data engineer might be working with some other priorities here, so when multiple hops are there, so priority is getting dissolved through the line, as well as, many ad hoc reports are coming. So every time as it goes through the batch processing, we are referring, most of the times we are referring to the same data again and again. So those data is taking much time to run, as well as delay decision making. So during the loan disbursement process, when there might be, okay, consider a branch use case. So every branch trade has to close by 5 p.m. So some other times the trade might have been raised by 4:45 p.m. So it has to be closed within that 15 minutes. So those cases we are getting delayed and those trades are getting missed out. So these are the reports before to that. So what does this report means is that when a ticket is raised, so whenever the client is expecting a report from us, they will raise a ticket on our platform. And once the report has been served and it is acknowledged by the client, we will close that report. So this is the general report generation time. And most of the time, the 25th percentile stands at 20 minutes. 50 percentile stands at 60 minutes, and 75th percentile stands at 220 minutes. So this is actually way too higher limits. We should not have taken this much time, but this is how it was before. On the other hand, the other problems is that communication gap. So clients are actually communicating to the business users. So there might be some jargons which data engineers might not be aware of. So because of that, data engineers might give some reports which wasn't as expected by the clients. There might be to and fro communications. So because of the same reports has to be fetched multiple times, and data quality issues as well. So whenever they are asking for some reports, certain filters has to be applied on that reports, and we are missing out on those reports because we don't know what is the communication actually happened between client and the business team. So when it comes to us, they simply say, give us the disbursement report. So there we might be missing out some filters, and when it reaches the customer, they will tell us like this report has to be filtered out, and there again we have to go through the same process all through again, and then we have to refetch the data and we have to give them. So again, so these are the number of iterations which went through for each ticket. So again, you see, most of the times, so every report took more than 6 iterations to get the circle closed. So what we used is that, so these are the 3 major sources currently we have. So Postgres and MongoDB are major source, and CockroachDB, rightly, we are working on a new product. So from these 3 sources, so from Postgres, we are using Debezium connector to fetch the CDC data. And from MongoDB, we are using Atlas connector, so everything is connectors provided by Confluent. And CDC, for CockroachDB, they have an inbuilt CDC, so we can configure it in the CDC CockroachDB itself. They act as a producer, and they will push the change to the Kafka topics. So once the data has been received in the Kafka topics, so we have a we have a consumer which is running in a Kubernetes. So what this consumer does is that it will fetch message from all the topics, and it will write it to the Redshift. So here we have 2 kinds of tables. So one is CDC table, and the another one is snapshot table. So CDC table is that we are capturing all the CDC data which is happening in the source system. So this CDC table will power our data warehouse tables, both fact and dimension tables. This will help us enable different SCD in our warehouse table. So this CDC table was already captured before, but now through unified layer we are capturing it, as well as we have snapshot table. So this snapshot table is just a replica of the source tables. So whatever having in the PostgreSDB, the same table will be present in Redshift as well. So we will poll Kafka topics in a micro batches. So every 3 seconds or 2 seconds, depends upon the use case, we will write that message to Redshift. So in a single flush, we are writing CDC table in insert way, and then snapshot table, it is in the merge format. So we are uploading both of these. As there is no overhead here, so we are okay to write the tables in two different Redshift tables. So here again, one more benefit here is that previously, when they have to look at the live data in RDS format, they have to go through the read replicas. So we have to manage the users there in the read replicas on the RDS side, as well as there are users who are accessing data in the Redshift. So we have to manage users in two different areas. Now, whatever the queries which are routed to, or whatever users who are using the read replica of the source system, they are now routed to use this snapshot table. So this helps us, with the governance as well as user access process. So once the table has been received in the Redshift, we use the tables to serve reports as well as dashboards. And how this solved our business use case is that, so we have data hub which will store the metadata of all our data warehouse tables. So generally, while creating the tables, we will give description for all those columns. That description will be fetched into data hub. If some table misses any description, we are using AI to generate description, and that particular table owner will be notified that this column has been given metadata, temporary metadata by AI, so they will be given SLA to give a proper metadata for the table. So we will use that metadata, and we have our own text-to-SQL model. It is in a version 1 now. It is RAG-based text-to model. So that metadata will be used by this text-to-SQL model. So those business users can use these text-to models, and they can look for details which they necessary, so without coming to the data engineers. So this is at a high-level architecture what we have done to solve the business use case. So let us jump a step deeper and look at, so we faced scalability issues at many places. Let's look at how we have solved it. So if you look at this, so we have considered two sources, so Postgres and MongoDB. So these are the tables in Postgres, and we have collections in MongoDB. So when it gets into Kafka systems, so we have created a topic for each table and each collections. To maintain the ordering of the events, we have maintained it with the 0 partitions. We have maintained replications, but the 0 partition is sufficient for us to handle the throughput currently. So again, through connectors, we will be populating the topics with the CDC data. So once data receives into CDC, we have to create a consumers, so that consumers have to fetch data from. So again, there might be different, within data engineering, there are different teams which work with the different products. To give them a single unified interface, so we ask them to configure a config file. So what that config file contains is that they have to give the consumer group properties. What is the consumer group name? What are the topics should be polled by that particular consumer group, as well as what is the number of replicas. Here replicas means the number of consumers to be contained within that consumer group. So those kind of details will be given in the config file, as well as we have given option to specify them. So what is the poll interval, or what is the flush interval? So every 3 seconds it has to write the data to Redshift, or is it like every 5 seconds is fine? So based on the use case, we are giving those configurations in this config file. So once this config file is pushed to Git, we have a Argo CD. This takes care of the Kubernetes deployment process. So once this pushed to Argo CD, we have a Helm charts that will have the consumer code as well as the Kubernetes deployment files. So this Argo CD will use those config files, create a new Docker image, and then will use that image to deploy the Helm charts into Kubernetes cluster as a Kubernetes deployment. So this Argo CD will take care of Kubernetes deployment. It makes sure the deployment is up all the time, and the deployment will take care that the consumers are running throughout. So this way we ensure that the pods, the streaming process is running throughout without any failures. So similarly, there are multiple ways. So if you have high throughput topics or high throughput tables at the source, you can club those and you can give configurations accordingly. If you have low throughput tables, so you can club like some 8 or 10 tables. 8 or 10 tables with the 2 consumers, and you can populate it accordingly. That is based on the use case. So once the data comes into, within these deployments, we have consumers running. Those consumers will write the data into Redshift. Again, we faced another scalability issue here. The issue is that we have ETL, the streaming pipelines, and other ad hoc workloads. Everything runs into the ETL Redshift server, which sometimes creates a trouble for our use cases which has stricter SLA, or use cases which is powering our UI. So to solve that, what we use is that we use WLM. So in the it's a workload management. So we have given highest priority queues for this streaming queries, as well as we are using RI3 nodes. RI3 nodes comes with a separate compute as well as separate storage. So here, as compute and storage are segregated, we are creating other serverless compute nodes. So through those compute nodes, through data sharing, which is an inbuilt capability provided by Redshift, so the data will be residing in one place, and we are sharing it to other areas through through added compute. So this is how we solved our use case. Thank you.
Hi. So I am Arghya Mukherjee, and I have one question, is when you are ingesting the Kafka topics directly to the Redshift, I think Redshift is very, the cost of the Redshift is high, right? So if you ingest like every topic into the Redshift cost will going to shoot, right? So why couldn't have an architecture where only the real time, the data that is required for the real time, those events are streamed into the Redshift, but the others, like for example, the batch reports and all, that can be stored into the, like for example, S3, and from S3 we can actually we know that like which are the topics that are important. In that way, we could have reduced the cost a lot, right? But that is my question.
Okay, I got your question. So initially we tried with S3 sync connectors as well. The issue we faced is that, so consider, so you are getting a message now. So within 3 seconds you are not getting, so 3 seconds is our default flush interval we are maintaining, so I'm checking to. So if you didn't receive any further messages, what Redshift, if you're using Redshift as a sync, what it will do is that when there is one message, it will be written into the Redshift through insert statement. Whereas in case of S3, you cannot have that low latency because S3 is a file system. So it has to open a file system, it has to open a file IOPS. So whenever records comes, it has to keep that file pipe open, so it has to keep accumulating the records to that pipe. So every 3 seconds, it cannot write it cannot close that pipe, and it has to write the file back to S3. So if we keep doing that, so for one record, we end up in one file. So as it is a file system, it does not have that capabilities. And coming to the another question, so you are asking about the increase in cost with Redshift compute. So we have a Redshift already provisioned for D-1 workloads, dimension modeling workloads, which we are using already before getting into streaming. So when we get into streaming, we didn't increase any computes or something. Streaming is happening as it is in the same compute itself. Just we used a WLM queue and we gave this streaming queries the higher priority. It was running well till that time. When more workloads started coming from different products, there it mostly 90 to 95% of the times it worked well. We faced no issues. Where we faced issues is that so the products started powering their UI from our Redshift tables. That is when those queries has to be completed before the UI pages loads. That is where we started facing issues. And for those critical workloads, for which the SLA is lesser, only those workloads we have migrated into a separate Redshift compute. So mostly 95% of workloads which runs in our existing Redshift cluster which we are using without any increase in compute. So this compute is able to handle our workloads. Only those which has a stricter SLA, through data sharing, we are just exposing that data to the another serverless cluster, and they are using it from there. So on the cost side, we don't face any hit. Any more questions?
Hi, thank you for the talk. If you could go back to the slide number 3, please. It's where you showed the old architecture. I think it was 4, yeah. Yeah, here you mentioned that the ad hoc reports take a lot of time, right? So which stage consumes most of the time? So is it fetching the columns that are already not there via batch ETL, or the columns are there, just transformation takes more time?
Transformation takes more time. So you see, first the report comes, we might have given the transformation doesn't change. The report might have taken some 5-10 minutes to fetch. We would have given them some report. They will come, so this filter has to be added on this column. Again, you see the transformation doesn't remain same, just a filter is getting added. So this is how it was earlier.
Okay. So
those guys know the business, we know data terminologies.
Okay, all right. Just a follow-up question to this. So since you're fetching real-time data for these ad hoc reports, how are you managing the transformation real-time?
No. Here again, so once the data has been brought into Redshift, we are giving those, so mostly the transformations are simpler here. Only the filters which they are applying is matter. So now this business users know basics of SQLs. They doesn't know to write a complex subqueries or something. They know how to write a SQL query with filters. Those things they know. Again, so if you look at a loans table, now any payment is happening, that will be happening against an EMI. What we'll do is that when populating that column, we will be calculating what is after that payment, what is the principal outstanding, we are just doing some pre-calculated fields which are stateless, which is applicable to that record alone. We are doing those calculations and creating a view to them. So this way, the calculations are eliminated. So they can just send a simple select query and they can fetch the reports they wanted. So now we are not doing the reports. They are doing the reports. Only when they are struggle, 1 or 2 tickets will come to us.
All right, thank you.
Yeah, thanks very much.